Hello everyone. We will now talk about the inverse tangent function. As with the sine function and the cosine function, we first run a horizontal line test on the tangent function, and if we end up using the entire domain of the tangent function and draw the horizontal line, we will see that it will not pass. Therefore, we will restrict the domain of the inverse tangent function to within one period, which is from negative pi over 2 and positive pi over 2. Therefore, the tangent function y equals tan of x will have an inverse function only within the restricted domain of minus pi over 2 comma pi over 2. And remember that at minus pi over 2 and pi over 2, we have the vertical asymptotes of the tangent function running, so they are not included within that interval. Therefore, you cannot come up with an angle measure for an inverse tan function, which is negative pi over 2 or positive pi over 2, but it can be any other angle within this interval. Let's define the inverse tangent function here, denoted by the notation tan with a -1 or -1 as the superscript. It is the inverse of the restricted tangent function y equals tan of x within the interval of negative pi over 2 and positive pi over 2. Now, please make a note that negative pi over 2 and positive pi over 2 are not included in the interval. So any other angle measure within this interval would be included, however, not negative pi over 2 and positive pi over 2, because those are the angle measures where the vertical asymptotes of the tangent function would lie. Now in equation form, we write it as y equals inverse tan of x. Now another way of referring to inverse functions would be as arc tan or arc sine, arc cosine, and so on. That's another way of referring to an inverse function. So y equals inverse tan of x means tan of y equals x, where y would be an angle measure. Again, to remind you that in an inverse function, the input is a ratio. So we could input any ratios between negative infinity to positive infinity. Remember that in the tangent function, the ratios rise indefinitely all the way to positive infinity on its right-hand side vertical asymptote, and it drops to negative infinity along the left-hand side vertical asymptote. So we can put in any ratio within this interval as an input to the inverse tangent function. However, the output values would only be values between negative pi over 2 and positive pi over 2, but it wouldn't be negative pi over 2 and positive pi over 2. But anything within that interval would be a valid output from the inverse tan function. The process of graphing the inverse tangent function is the same as we used for the inverse sine or the inverse cosine function. That is, we take certain points of the tangent function, switch the x and y coordinates of each point, and graph those points on the coordinate plane built for the inverse function graph, and then connect those points to come up with the graph of the inverse tangent function. So the inverse tangent function graph will take this shape, the one shown in the picture on the right hand side. Again, the x-axis has been scaled from negative infinity to positive infinity, and along the y-axis we have negative pi over 2 on the negative y-axis and positive pi over 2 along the positive y-axis. However, you see there are some horizontal asymptotes. So on the inverse tangent function, we have horizontal asymptotes at negative pi over 2 and positive pi over 2 because they are now represented along the y-axis, whereas in the tangent function we had vertical asymptotes at negative pi over 2 and positive pi over 2 because those were represented along the horizontal x-axis, right? Let's go through the steps of finding exact values of the inverse tan of x or arctan of x. We first write it in the form of an equation as theta equals inverse tan of x and remind ourselves that we are looking for an angle measure whose tan function gives a ratio of the given measure that x is. So we write it as theta equals inverse tan of x, and in step 2 we rewrite that same equation in the form tan of theta equals x, which tells us what is the angle measure whose tan ratio is whatever value of x that has been given to us. And we will come up with a value of theta within this interval range minus pi over 2 less than theta less than pi over 2, and in the final step we will refer to a table of special angles. Now for the inverse tan function we have been given angle measures between negative pi over 2 and positive pi over 2. However, because those two angles specifically will not be a part of the solution, they have excluded those from the table. So we will have special angles between this interval starting from negative pi over 3 to positive pi over 3. However, observe that they have not included negative pi over 2 and positive pi over 2. And below here we have the corresponding tan ratios. So we are going to refer to this table, find the ratio that we are working with, and then locate the corresponding angle measure, right? Let's work through an example of finding the exact value of inverse tan of negative 1. In step 1, we write it in equation form as theta equals inverse tan, also referred to as arctan of negative 1. The input to an inverse function has to be a ratio. So negative 1 is a ratio. We have to find the corresponding angle measure whose tangent has a ratio of negative 1. And we write it again as theta equals inverse tan of negative 1. In step 2, we write it as tan of theta equals x, where theta would be an angle measure between negative pi over 2 and positive pi over 2, but those two angles in particular will not be included in the interval of angles possible. So we write it as tan of theta equals negative 1, looking for what angle would have a tan ratio of negative 1. In the next step, we will open up the tangent function table with special angles within this range of negative pi over 2 and positive pi over 2 and find the corresponding angle for negative 1, right? Here we are in step 3 with our table of special angles starting from negative pi over 3 to positive pi over 3. However, they have not included negative pi over 2 and positive pi over 2 in this table because they are not a part of the interval. So let's first look at the ratio that was given to us, which is negative 1, and we see the corresponding angle measure is negative pi over 4, and that is the solution for this problem. The angle within the interval negative pi over 2 and pi over 2, whose tangent function would have a ratio of negative 1, is negative pi over 4, which is this boxed column of the table. All right? Now we will talk about the inverse of the reciprocal trigonometric functions, which are the cotangent, cosecant, and the secant functions. By this time, we should have a pretty good grasp of the concept behind inverse functions, that their domain has to be restricted in order for us to obtain an inverse function, how to find the exact values of an inverse trigonometric function, what the graphs look like, how to obtain the graphs by switching the x and y coordinates of the trigonometric functions and use them for the inverse function graphs, and so on. So the same apply to the inverse functions of the reciprocal trigonometric functions as well, but let's go over the restriction of the domain for each of these functions. We'll start with the inverse cotangent function, denoted as cot with a -1 as its superscript, and the restricted domain is between 0 and pi, but 0 and pi by themselves are not included within this interval, but anything between this interval would be an acceptable domain. So y equals arc cot, or a y equals inverse cot of x, means cot of y equals x, where 0 is less than y less than pi, and -infinity to +infinity for the x values. That means the ratios that are input into the inverse cotangent function could be anywhere from -infinity to +infinity. However, output values, the angle values, would be a measure between the interval 0 and pi, but not including 0 and pi. Let's look at the one for cosecant. The accepted domain for the cosecant function would be -pi/2 less or equal to x less than 0, or 0 less than x less or equal to pi/2. You have to remember that over here, or means the union of these two interval of values. So y equals cosecant or inverse cosecant of x means cosecant of y equals x, where y is a value between -pi/2 and 0, or 0 to +pi/2, and over here pi/2 and -pi/2 are included, but 0 is not included. As far as the x values are concerned, it's x less or equal to -1, or x greater or equal to +1. So what this means is we can input values of the ratios into the inverse cosecant function, which could be less or equal to -1 or greater or equal to +1. However, the y values would only be within this given interval. It would not include 0 in the interval. As far as the secant function is concerned, look at its restricted domain. It's 0 less or equal to x less than pi/2, or pi/2 less than x less or equal to pi, and expressed in equation form, it's y equals inverse secant of x, means secant of y equals x, where 0 less or equal to y less than pi/2, or pi/2 less than y less or equal to pi. And as far as x is concerned, it would be x less or equal to -1, or x greater or equal to +1. Here's a picture of all the graphs of the inverse trigonometric functions put together, starting with the inverse sine function with its domain and range intervals given. The next one here is the reciprocal of the sine function, which is the cosecant of x, or rather inverse cosecant of x with its domain and range. Then we have below the inverse sine function, the inverse cosine function, whose graph looks like this, its domain and range. And next to it is the inverse secant function graph, which looks like this over here, as in this picture. And then in the last column, we have the graphs of the inverse tangent function and the inverse cotangent function with their respective domain and range intervals. At this point, we will go over the inverse properties of the different trigonometric functions and their inverses and look at what we get back when we create composite functions with the sine and the inverse sine, or the cosine and the inverse cosine, likewise tan and the inverse tan functions. So over here, the sine function and its inverse, when we input an inverse sine of x to a sine function, we should get back x, which is a ratio. Recall that x that was input into an inverse sine function was a ratio, and the evaluation of the inverse sine of x would be an angle measure. So essentially, you are inputting an angle measure into the sine function, and you should get back the ratio as the calculated value, as the evaluated value. So sine of inverse sine of x equals x. However, it has to be within this interval of -1, +1 inclusive. If you input the sine of x function into the inverse sine function, you should get back x. Now, for the sine function, this x is an angle measure. All right, and sine of x will evaluate to a ratio. So you're inputting a ratio equivalent to whatever sine of x is into the inverse sine function, and that should give you back the angle measure. The output from an inverse sine calculation is always an angle. However, the angle measure should be a value between -π/2, +π/2, which is the restricted domain for the sine function. The same applies to the cosine function. Cos of inverse cosine of x equals x, but within the interval -1, 1 inclusive, and the inverse cosine of x of cos of x equals x for x in the interval 0, π. So this value x would be an angle measure within this interval of 0, π. For the tangent function, tan of inverse tan of x equals x for every real number x, and inverse tan of x equals x for every x but within the interval of -π/2, π/2. So these represent the restricted domain, correct? -π/2, π/2 for inverse tan. For inverse cosine, it was 0, π, and for inverse sine, it was -π/2, π/2, correct? So this is a summary for looking at the inverse properties of the different trigonometric functions.